my name is Jiri Dobes and Head of Solutions in Johnson Labs. I will be talking today about automatic miming of adverse drug reactions from social media posts and unstructured chats. So we are Johnson Labs. We are 5 years on the market, and we focus exclusively on NLP in healthcare sector. Why in healthcare? Because the language is different in healthcare or pharma or clinical practice than in normal English. You see, there are different vocabulary, different words, different structure of the sentences, there are abbreviation, etc. So technically it is challenging, and also it is challenging on the process side. So for example, how to work with PHI data, or how to work in hospitals, how to get even access to the records. So let me first talk about the motivation for mining of adverse drug reactions. So what is adverse drug reaction? There is something which is called adverse event. It's any untoward medical occurrence in patient during clinical trial or during normal post-marketing time of taking drugs, but it may not necessarily be related to the medical product. If there is at least suspected relation between this adverse reaction and the drug, it's called adverse reaction or adverse drug reaction. It also includes usage of the product outside of the terms of marketing authorization, like, for example, off-label use, which means using the drug which was not intended for, or misuse, abuse, overdose, etc. It may or may not include medication error. So if there is medication error, it may not even lead to the adverse event or adverse drug reaction, or it may happen that there is adverse drug reaction. Adverse drug reaction, it's a really serious and widespread issue. It's like 100,000 fatalities in the US every year. It's fourth most often cause of death in the US. It's very expensive to cure, and like there are tens of percents. It's very often to experience adverse drug reaction. It's not something which is rare in any case. Yet the adverse drug reaction are mostly underreported. So it's usually it's like 1 in 20 is reported, and in the case of serious adverse drug reaction, it's roughly 15%. It's reported, all the rest is not reported. There is something which is called pharmacovigilance. Pharmacovigilance deals with the adverse drug reactions, and this is during the post-marketing phase. Why we need to check for the adverse drug reaction post-marketing phase, so during the time where the drug is already on the market, because during clinical trials, not all adverse drug reactions are found, because with not enough people in a clinical trial, because then the rare events are not found, or too short duration, which means that the events which takes long time are not demonstrated, or not all drug-to-drug interactions are tested, or off-label usage. All the pharma companies or marketing holders are required to report adverse drug reaction. In general, they are required to organize data collection systems. They are required to screen the literature. They are also required to screen internet or digital media, but only under their management. They are also required to investigate digital media if they are not under their management, in case of they become aware of the potential report. In regulatory groups, there is a lot of discussion about in necessity of screening of general social media, and there's also a lot of research. We, like every pharma company, they usually have the multi-channel unstructured data. There are channels where the patient, doctors, and other stakeholders are discussing with the pharma company, or there is a flow of information back and forth. There is also a lot of notes, transcripts, or literature. From all those sources, we are able to mine the adverse drug reactions. So let's look to how does it work. So it's basically a three-step process. First, we collect information from different sources. Then we filter the information, which means dealing with synonyms, dealing with different names of drugs, maybe dealing with different languages, and then preprocess the data. And then third step is classification and extraction. And I will be talking only about this third step during my presentation. So text classification, which means does it include the adverse event, entity recognition, what are the drugs and what are the adverse drug event in the text, and is there any relation between the event and the drug. So for example, this is, I will be showing this example several times during the presentation. I experienced fatigue, muscle cramps, anxiety, aggression, and sadness after taking Lipitor, but no more adverse after passing Zocor. So first of all, it has adverse drug reaction. So there is a classification, then extraction of the adverse events, which is fatigue, muscle cramps, anxiety, aggression, sadness, and drugs, Lipitor, Zocor, and a relation extraction between each of the occurrence of the drug and each of the occurrence of the adverse drug event. So for Lipitor, there are detected relations, while for Zocor, there is no relation between the drug and the drug adverse drug event. So all the talk will be based on the paper what my colleagues published just like 1 month ago on the international workshop on health intelligence. And it's called Mining Adverse Drug Reaction from Unstructured Mediums at Scale. We show the novel solution for the classification, DEM entity recognition, and relations. And we achieved state-of-the-art result for CADEC dataset, and the state-of-the-art results for few datasets on the name entity recognition. And then we show that in case of simpler method, what we present, if the dataset is enriched with additional data, we outperform state-of-the-art benchmark. There is combination of the pipeline. So this is pipeline for all classification and entity recognition and the relation extraction. Let me first describe this classification pipeline. Start with document, do the BERT embedding. Then there are several ways how to achieve the document embedding. And then classifier. Classifier is here fully connected neural network. And it is classifier only to 2 classes. And then, so this is the classification, then name entity recognition. There is starting for document, going through tokenization, then word embedding and name entity extraction model. And word embedding can be GLAV, can be BERT, and we show the results for both of the cases. And finally, a relation extraction, which is coming from the name entity recognition, and then it can be either taking features from the document, from span and context embeddings, and build a fully connected neural network, or take document context and build fully connected neural network based on the BERT model. All the details are in the publication I had on the previous slides. So for the classification, we outperformed the state-of-the-art for CADEC. It was 81%. We achieved 86% F1 score. For adverse drug ADE dataset, we are close, let's say, close to the state-of-the-art. It was like 85, 86% F1, while state-of-the-art it's 87. Why it's CADEC? It's more complex case, so this is probably the reason why the BART embeddings is advantage here. If we go to the name entity recognition, again the BART method, it shows we achieve state of the art. But the interesting case is here. If you compare the result from using BART embedding and GLAF embedding, because in GLAF embedding we are almost the same results. So, for example, for CADEC datasets is 78.7, while for GLAF embedding it's 77. So it's like the difference is very small. And if you look to the speed up and for inference, it's like BART is 12 to 15 times slower than GLAF embeddings. So it is possible to use the GLAF embeddings on a small expense of accuracy while achieving like big speed up. And this is aligned with another paper what we published on name entity recognition last year. Finally, relation extraction. For the relation extraction, if this is quite simple method, it's simpler than what was published in the state of the art. Here it's F1 80%, while the state of the art is 83, right? But so it's performs more or less on par with the state of the art, a bit lower. But if you enrich the data set with additional examples, and also you make the data set balanced, then you greatly outperform current state of the art. All right, let me talk quickly about the implementation. We implemented in Spark NLP. Spark NLP is the library what we develop, and we focus on the accuracy. We are now holding 9 records in the most accurate method with various benchmarks in paper with code, and there is, I think, another 8 coming, which is not yet included in the benchmark. For speed, everything is programmed in Scala. We partner with Intel and NVIDIA to make it work fast, even on single processor, and the scalability which is given by the underlying Apache Spark technology. In Spark NLP, it's more or less everything what you need while developing modern NLP solutions. We support many languages, like many models, and also almost all models are trainable. For Spark NLP for healthcare, this is what I will be talking about the implementation. We more or less replicated what we did for Spark NLP. This is the commercial extension. And only there are different algorithms due to the differences between the normal language and the healthcare specific language, and also in use cases, because the usual use cases for in healthcare are a bit different than for generic English language or natural languages. It runs on air-gap environment, no need on internet, can download everything upfront. You're not sharing data with us. So I will be talking now about the implementation in Spark NLP for healthcare of the example what I had in the previous slide. Right? So we will do the classification, we will do the entity extraction, and we will do also relation extraction. So this is the real example. It's not only a snippet of code, but it is full code. because I believe it's more useful for you to see the full code, because there could be some hidden tricks which, if I would present here only a snippet of code, you wouldn't see that. This is for, if you copy paste this in Google Colab, it would run in Google Colab. So first of all, we set up the Google Colab, we upload the license key because this is licensed software. Then the license keys are updated into environment. Then we install PySpark and Spark NLP for healthcare. And also something which is Spark NLP display, which will be showing the graph what was on the previous slide. Then we establish, we import the libraries, and we establish the Spark session. And in this case, this was in Spark NLP and Spark NLP for healthcare 3.4.2, which is the most recent release as of March 2022. Then need to set up document assembler, sentences, tokenizer, embeddings, etc. I will not go through each of those lines, but in the end, basically you need to set up the pipeline. So this is the classification pipeline, so document assembler, sentencer, tokenizer. There is BERT embeddings, sentence embeddings. Sentence embeddings in this case are done as an average from BERT. And then there is deep classifier, which is the only fully connected neural network. And this is already trained, so this pipeline is only for inference. Then we have the pipeline. We feed the pipeline with empty data, which means basically just establishing the pipeline, and then we use light pipeline. Light pipeline, it is advantage that it can go, it's faster for execution, and it can process not only a Spark data frame, but it can also process list. And here, if you just run it on the sentence that I was talking about before, this I experience fatigue, etc. Then you call annotate function and check the class, you get true, which means presence of the adverse drug reaction. If I go to the next slide, here is the rest of the pipeline. So words embedding. Before I was on the previous slide, there was embedding of BERT embedding. Here there are clinical embeddings, which is glove embedding. Then there is part of speech, this extraction. Then the clinical model for name entity recognition for advanced drug events. And then we convert it to need to do the merging of the name entities. And then do the relation extraction. So then setting up full pipeline, again starting from the assembler, sentences, tokenizer, embedding, name entity, part of speech and name entity tagging, chunker dependency parser, and relation extraction model. Again, you fit with the empty data just to build a pipeline and create light pipeline out of it. And then we annotate the text. The text is the sentence shown on the previous slide. Here I would like to show the results in some nice table. So it's just organization of the data in a nice table. And then we plot the results. So for each line, you see that the difference is here in chunk 2, which is the first one is Lipitor and fatigue. The second line is Zocor and fatigue. And here you see that the relations between lipitor and fatigue is set as a 1, which means there is adverse drug reaction, while here in Zocor and fatigue, the relation is set as a 0. Right? So here there are all the entities and all the both the drug and adverse events, and also all the reactions. And finally, I would like to display the table which was on the previous slide. So you just call the relation extraction visualizer, and you visualize the results. And this is first because it's only one sentence, so this is or one record, and you get exactly the same picture that was shown before in one of the slides. All right. We have also real life reference. This is what our customer from OmniHealth, they were presenting in last fall in NLP Summit, adverse drug event detection using Spark NLP. Right, so lessons learned. We did NLP system for a classification of presence or absence of adverse drug reaction, extraction of the adverse effects, and classification of the relations. We established new state-of-the-art for a few benchmarks, and we implement the solution into Enterprise GS Spark NLP for Healthcare Library. And all the models, what I was talking about, they are included into pre-trained model set. So they are available as a standard models in Spark NLP for Healthcare. Okay, thank you very much for your attention.